how it goes. Anyway. And I'll try not to trip all over myself on the cord. Very nice to see you. Apologize for the delay. So last time we kind of ended, we were talking about the wave equation. So we were talking about the three fundamental equations. But in particular, we were talking about the wave equation, which was something like two derivatives in the t direction equals the wave speed squared times two derivatives in the x direction. And this is a very old classical equation. And there's a solution. So there's different ways you can conceptualize this. So you can think of it as a string with like fixed ends that you're looking and running around. Or you can just look at this on the entire real line. You know, think of maybe an infinitely long string with no boundary condition. And there's a solution that goes all the way back to a person named Dale and Barry. Who basically just noticed that if you take any pair of functions that admit, you know, two partial derivatives that are continuous, what we call C2 functions. Let's call those functions F1 and F2. Then basically you just kind of get a solution to that equation, you know, for free, where time or maybe you want to start time at 0 and you want to let the string of the space x be infinite. And you can kind of imagine this being like a wave traveling to your right and that being a wave traveling to your left, but you put the string in sort of opposite. And I think in a homework exercise or a just sort of like a practice exercise, I asked you to show that the following also satisfies this equation, right? So you can take 1 over 2c. And then sort of take the derivatives according to the fundamental theorem of calculus. So I think first there might be a little bit of tension here. So where's the F1 and F2 in this picture? Great question. Yeah, you kind of want to split this up, right? So you could maybe write this as plus 1 over 2c, and you go from minus c to 0, or you could pick any number at all that's in a domain, but as long as the domain is infinite, it doesn't matter. So I just thought that was kind of interesting, you know, this question came from a different source, And so maybe it's kind of interesting to compare it to Dahlenberg's result. Like you can, the solution is whatever you want, and you'll see different mathematicians presenting solutions in different forms, even though we're talking about kind of like the same thing. And you'll see that in more nuanced situations as the class progresses. So I don't think I'll actually do the work and show that, these things solve the equation. I think you could calculate the partial derivatives and kind of see that it works out. But you can see how the partial derivative with respect to t gives you that factor of c. So you need to multiply on the x side to make them equal. Okay. Any questions or comments?
You might want to look at this after class, but you wanted us to show that
this would solve the equation. Solve this equation.
I kind of did the math through, but up to this point, I can figure out how to progress to
Yeah. Okay. Well, maybe we could talk your future class.
There we go.
For today, I want to switch gears a little bit. We've introduced the three fundamental equations. We've shown you solutions either on the board or through homework exercises that are coming due. And we'll speak about how to find solutions with all kinds of different boundary conditions. It's really the boundary conditions that make these problems difficult, not just finding a solution. But for now, I want to approach a slightly different topic. So I want to approach this idea of a conservation equation. Maybe we've got a question here. Yeah, so it's a shame about the audio. Maybe I've got it the wrong setting. I'll go back to this one that I think is the lavalier, and I will just, when I can hear the video, I'll try to see what's going on, and I'll try to maybe, not be looking this way when I'm talking. Okay. So I want to introduce this with a physical model. It's another kind of toy model, but it's one that I like. So this is in chapter 1 of your reading of the applied book. It's also section 3.1 and 3.2 of the non-applied book. And I'll do it with a specific toy model, but it's kind of a general thing. And the idea that we're going to be looking at here is this is going to be oxygen concentration in a section of an artery, which for simplicity is going to be like a cylinder. And for even more simplicity, when you take any point x and you look at the cylindrical side, that should have a constant oxygen concentration, but the concentration can vary as X moves around. So that allows us to think of this as a one-dimensional spatial problem and one-dimensional time. So let's just say we're looking at a section going from A to B. And the units of U are something like mass over length. So U really does represent a concentration or a density. And therefore, if you want to look at the mass, the total amount of oxygen from A to B, you would look at this integral of the function U from A to B. And the integration basically multiplies by length, so the units of the integral should just be mass. And of course, as time goes on, the mass can vary. The idea is that there is blood flowing through the artery. There's no oxygen coming in or out along the walls here. New oxygen can come in from the left, and as the blood's coming in, oxygen can leave as the blood's going out, but otherwise it's not being created. Okay, and so we introduced something called the flux. And you have two different textbooks and they label it two different ways. So I'll just sort of pick one. Also, one of your textbooks uses X and C, and the other one uses C and X. You'll sorry about that, but whatever. So let's call this the flux. And what this is, it's a density that tells you the instantaneous change in concentration. So the units of Q are also going to be mass over time. Because, the flux, QAT, tells you how much oxygen is entering at time t from that blood flow. And the flux here tells you how much is leaving. The flux here tells you how much oxygen is crossing that boundary at that point. Okay? And so here comes the conservation law. So if you look at the total amount of oxygen, and you look at the total derivative, right? The derivative of the mass with respect to time, that should be, physically, what is the total change? How much is going in at that instant, minus how much is going out at that instant. That's what we do with the derivative. So I need to say how much is going in minus how much is going out. And so by the fundamental theory of calculus, so you can think of t for a moment as being a fixed point in time. And by fundamental theory of calculus, this will be class exercise, so take 10 to 30 seconds and write down what interval is this equal to by the fundamental theory of calculus. I'll go ahead and sneak in the negative sign. So having given you a few moments to reason it through, I'm willing to write it down, but if anybody has a guess, we may proceed.
derivation integral from A to B of dq dx. Yes.
So is this for b minus a, thinking of this as a function of x, fundamental calculus tells us that we can evaluate this integral, by looking at the inputs of the antiderivative, assuming, of course, that the flux is differentiable. So we kind of pull out the assumptions that we need for our model as we go along. That's a physically reasonable assumption.
Right, the flow.
Well, I don't know about that. We certainly don't want that to happen. So we certainly don't want that to happen. Okay, so this is the first form of the conservation equation. We need to work on it a little bit. On the other hand, math has an integral form. Math was integral from A to B. And then we take the derivative of the mass. So here's the part where we kind of maybe skip over something from analysis class, which is that if this function u, if this function u has a certain property, in particular, like if u is differentiable, which we should assume that it is, then it's legitimate that you can move the derivative, to the inside. Basically there's a theorem that says, like, as long as this integral is what? Like absolutely convergent, and this function is continuously differentiable, you can interchange the order. It's basically a theorem on interchanging the order of limit and the derivative and limit of the integral. Yeah.
So none of the is total mass of object.
Region from A to B. Yeah.
Why do we integrate with respect to the
Oh, yeah, you don't. You do differentiate with respect to t because it's changing. And here you integrate with respect to x because you're specifically looking at it. So thank you. So now we're good. So now let's just sort of take this side and that side, of the equation, those two things that are equal to each other. We can end up with and then plus, right? So there's sort of the next form of our conservation equation. This is, all coming from a conservation of gas. And then, what am I doing? I'm integrating a function from A to B, but this holds good for any pair of points, A and B, right? You've got some section of a cylinder, and you take any A and B you want, like here to here, there to there, whatever. This whole argument is still good. And so let's assume that U and Q are differentiable and their derivatives are continuous. So this is a continuous function. And if it's true that the integral from A to B is 0 on every single interval from A to B, what do you think you can conclude about the function itself? Yeah. so you can conclude. This one's shorthand for that sum, right? T for the partial derivative and suppressing the variables. Why is that true? Well, suppose that there were some points where the integrand was non-zero. Then by continuity, there must be a small interval around that point where it stays non-zero. Your continuous function, what continuous means is that if you have a fixed value, your continuous, like, then your value can't change too fast. Right? So there must be, and you can do this formally analysis, but the idea is clear. So there must be some interval where, you know, where it's definitely not zero. And if this, at some point, if it was positive, then it stays positive. At some small interval. If there's a point where the integrand is negative, it stays negative. Some small interval. So just choose A and B to be within that small interval, and then you'd be integrating something that's definitely positive or definitely negative. It would not be zero. So it's important that the integrand is continuous, and that this works for A and B, but if you have those two conditions, you can automatically conclude. And so this is the equation that's called the principal equation. This is famous in physics. Your book also calls it the continuity equation. As you're noticing in this class, I'm building up a physical model for that situation. I'm going to derive an equation and show you how to solve it. Okay, so but the problem is you've got, you know, you've got U and you've got Q, you've got the mass and you've also got the flux, and so you'd like some way to relate the two, and so here physics helps us again, right? So flux, generally speaking, this is supposed to be concentration times velocity. You know, at least at the level of if everything is constant, then you get the formula like you want to do in physics. And if you make the assumption that the concentration, remember UXT is the concentration, if you make the assumption that the concentration is independent of the velocity of the blood flow, which is reasonable if there's not much oxygen in the blood compared to the total mass of the blood, you know, small variation in the small volume are not going to affect the flow. And you have to be in a small region of an artery anyway to make it really sound. So that's not like a completely unreasonable assumption. And if you do that, then you end up with a linear relationship. So I won't write the assumption down, just take it verbally. If you assume concentration is independent from velocity, you end up with Q is actually equal to your concentration function times your function of velocity. So V is the velocity of the blood flow. And now you can simply substitute this in for Q and get a new equation. I'll do that, but I'll give you 30 seconds to do it yourself. So I won't make you volunteer the answer, but what I do after I substitute in u times v into q of x and just use the product rule, what I end up with is the following equation. Namely, partial with respect to u plus partial with respect times v plus u times partial with respect to v equals 0. And so this is called your linear conservation equation. It's an equation that comes from conservation of mass and with the assumption that the flux had a linear relationship. And that's why you call it linear conservation equation. So to this point in class, we took a toy model and we derived a first order PDE for, for its solution. And I'd like to speak about like how you would solve an equation like this. Of course, you can't really solve this without knowing V, right? You have to kind of measure the velocity, plug that into the equation, and then solve for U. But we can talk about the theory of how you would solve it. I could give you like homework exercises where I specify the value of V, and then you solve it that way. So on and so forth. Oh, and by the way, this kind of setup has a name. Advection. So this describes the motion of particles in bulk fluid flow, generally speaking. So this linear conservation equation applies to physical setups that involve advection, not just oxygen in fluid flow. So how do you make this? So I'm going to do some general theory. Around the following kind of equation. So u sub t plus d u sub x plus w equals 0, and w is allowed to depend on u. Did I write that down? So w can depend on x, t, and u. So in this linear conservation equation is a special case of my general theory with w being equal to u times v sub x. And so I want to tell you generally how to solve this type of equation, and so it applies to other kinds of models. And so how do you do this? So this is, the idea is to reduce to a single variable ODE equation and then solve it that way. So I'll even discuss, what that ODE theorem is that lets you solve it. And the reduction method is something called the method of characteristics. So what we're going to do in this setup is we're really going to reduce this to a system of two ODEs and solve those ODEs simultaneously. And that will give us the solution of the PDE on a so-called characteristic line. Let's get into that. So let me give you clearly the definition. So consider a function that sends t to x of t. You're thinking of this almost like a change of variable. So this is a characteristic. I call this equation a star. So such a function is a characteristic for equation star if it satisfies the following differential equation, namely derivative of x with respect to t is equal to your velocity function with x of t plugged in. And actually, if you have taken ODE, then you're familiar with this probably from Picard's theorem, the way that you do an iterative process to solve a first order ODE. So of course, the characteristic is only going to exist if a solution to this equation exists, right? So the setup is that V is given to you, or it's come from your own observation. V has two variables in it, but you want to cut out one of the variables by writing x as a function of t, and then solving the equation. So how do you solve this? So there's a technique from ODE called Picard iteration. And what it says is that given, starting with some t naught. So maybe let's write x naught equals x of t naught. So given that initial condition, sort of declaring that the value of x at t naught should be x naught. There is an interim about t naught and one about x naught. Where the characteristic exists. And you learn this like in the first week or two of ODE class. And there's another condition, which is that function v must be something we call Lipschitz continuous. But it's enough to assume. Like if you haven't seen that word before, it's easily Googleable, but it's sufficient for our purposes. That's derivative. And it exists. And is bounded. So without getting too lost in the weeds of what's technically required for the theorem or whatever, something called Lipschitz, and then, but it's enough to assume it's just differentiable with bounded derivative. And that will guarantee you a solution, and also it'll guarantee you a solution that's unique. And the way that you kind of prove that, again, not to get into the other class too much, but the way that you prove that is you substitute x naught, initial condition x naught, into this equation. Just integrate both sides, because now you're just integrating something with respect to t only. And the result, you call that x1, and then you substitute the x1 into the function now, and then x1 is now a function of t, so you still have a function of t, and you integrate both sides to find x2. And you keep on putting in your successive x functions, x1, x2, x3, x4. That's the iteration technique. And then what happens is that if you're Lipschitz, if you have this condition on bounded derivative, then the sequence of functions that you get will actually converge to a proper solution. So that was Picard's great idea there. And so it's a way to solve first order ODE. Okay, but anyway, so this tells us that a characteristic is always going to exist for this equation, at least for a short time. So how do we use that to solve the equation? Well, actually, first I'll give you like a little bit of practice with this concept. So here's this in-class exercise. I mean, it's kind of simple. At least it's concrete. So in a simple case where V doesn't depend on X, right? So find the characteristic. Or T0 equals 0 and X not just being a constant. So just checking that we understand the definitions, I guess. And I'll give you 30 seconds to do that. Okay, so I'll put it down there. The answer is so I don't need fancy Picard iteration method because V only depends on T, not on X. So I can just calculate the characteristic by direct integration. And conclude that in this case, X of T is equal to T squared plus BT plus X. So certainly this satisfies an equation with this characteristic condition. So the characteristics are parameterized by X naught here, right? So you really want a solution that is going to be on as much of the XT plane as you can. But instead, what we're doing is we're identifying a characteristic curve, and we're going to solve PE on that characteristic curve. But the upshot is I can switch around my initial condition and therefore solve it. Okay, so returning to the general theory, how do you solve this equation? So this is a method that's due to Lagrange. And so I'm going to define what we call the Lagrangian derivative. I'm not sure how common this is really in mathematics, but all it is the total derivative of this element. Remember that the partial derivative would just be like considering this variable only, the total derivative takes the legitimate calculus derivative with respect to t, including that dependency. So once they've shown that a characteristic curve exists, you can now differentiate this equation. And take 20 seconds to write out that derivative. Okay, so now I'll show you what I think is the answer. So you take the total derivatives of according to the chain rule, you'll be wanting to look at the partial derivative of u and then adding to it. You'll take the partial derivative with respect to x. And then you've got dx dt. So that's the chain rule from vector calculus. But you can see how we created the method of characteristics, because you kind of do this equation first, and then you realize that it would be nice if this were equal to v, which it is, because, you know, I presented this theory after the fact. So substituting that in, okay, u sub t plus u sub x times v. Right, and so you've seen that before in this prototip equation. So you end up learning that, you know, this total derivative plus w equals 0. Well, I should be careful because it's not really w, is it? It's w when you plug in a characteristic term. So I'll put a little tilde on it. So it's really w tilde is equal to w of t, you know, x of t. And it can also depend on u, right? So you're plugging in the characteristic term. So w tilde is a function of t. You're finding closely. So you're solving out the characteristic term. And I could even just call u tilde to be u of t of x of t. And then this equation simply becomes dt u tilde plus w tilde equals 0. Why do you care about this? Because this is an ODE, which you can solve with the Carr's iteration. You can solve it exactly the same way as we did the characteristic. And if you supplement it with this equation, dx dt equals v dx. This system of two ODE, if you solve this system of two ODE simultaneously, first solving this and then solving that, you have now. So here's a picture like of the domain of the domain of the xt, right? And you found a characteristic in that domain. And solving the system of ODE gives you a solution of PE on that particular characteristic. This is called the method of characteristics. So it's quite general, and it doesn't, it's not a formula, right? So this isn't a class necessarily with a huge amount of formulas. You know, there's formulas, but there's also, you know, general theory. That's general theory. It's sort of proving to you that you can solve this equation we just derived by reducing it to a system of two ODEs with the method of characteristics. If you were in a physical situation, you would need to measure that velocity v. You would need to use like a numerical solver maybe to get those equations and get the answer. Although in limited circumstances, you can actually find solutions, and you'll see that on your homework. So let's maybe try an example. I mean, this example will be kind of contrived, just to give you the idea, but let's look at what we've got. So let's type the following PE. So in this case, we have W equals 0 and we have V equals AT plus B. Let's supplement with the initial condition that U of 0x equals G of x. So in other words, we have specified a initial concentration and it changes over time according to the transform equation, with W equals 0. And so how can we do this? Well, we have already found, let's see, we've already found the characteristic. And we've already found it to be AT squared over 2 plus BT plus X naught. Well, the UDT equals minus W twiddle, right? And W and therefore W twiddle are both equal to 0. So that tells me that the derivative of U twiddle with respect to T is also equal to 0. So that tells me that U twiddle, which again was U of T and an X of T plugged in, was equal to some sort of constant, right? So this is U twiddle, its derivative is 0, so it must be equal to the constant. So which constant is it equal to? Well, just plug in T equals 0. If you plug in T equals 0, then you end up with U of 0 X naught, which is just equal to G of X naught by your initial condition. On the other hand, that's equal to C. So G of X naught is equal to C. Is that okay so far? Just sort of like play in the definitions. This was a constant, and because of the initial condition, plug in 0, get G of X naught. And so have we actually done anything? Well, kind of, yes, because you can actually solve this equation for X naught, right? You can say that X naught is equal to X minus A T squared over 2. Minus BT. And on the other hand, here, this is equal to X, right? So if I just take this equation, rewrite it, I get U of T X equals G of X naught, which is, G of X minus AT squared minus BT. And, this depended on initial condition X naught, but since I rewrote it in the form that doesn't involve the initial condition, this will still be good no matter which initial condition you pick. And we arrive now at a legitimate solution, at a solution to this equation with this initial condition, and I invite you to check it out. So that's, an illustration of the process of the method of characteristics to solve at least like a simple example where the velocity didn't depend on x. For more general cases, you have to appeal to Picard's theorem and numeric integration. So your references, check out chapter 3.1, 3.2 in Intro to PDE, and check out the corresponding section in chapter 1, you're reading for today from the applied. Okay. So thank you everybody for your time and attention, and sorry for going 2 minutes over. And I'll see you on Friday.